AI Agent Design. Hello, everyone. Today, I'd like to walk through how to design AI agent systems. An AI agent is not just a smarter chatbot. A chatbot usually gives one response, but an agent can take a goal, plan steps, call tools, observe results, and keep going until the task is completed. The core loop looks like this: goal, plan, act, observe, repeat, final answer. So the simple definition is this: agent equals LLM plus tools plus loop plus state plus control. Now let's start with the core framework. When I think about AI agent design, I usually break it down into 5 parts. First, goal and planning. Second, tool usage and execution. Third, memory and state management. Fourth, control loop and observability. And finally, safety, latency, and cost. The main trade-off is autonomy versus reliability versus cost. More autonomy makes the agent more flexible, but it also increases risk, latency, and cost. What is an AI agent? An AI agent is an LLM-based system that solves tasks through multiple steps. It can receive a goal, create a plan, execute actions, observe results, update state, and continue. A typical architecture looks like this. User goal goes to the planner. The planner selects tools. The tool execution layer runs the tools. The system observes the results. Memory stores useful information. The controller loop decides the next step. Finally, the agent returns the final response. The key difference from a chatbot is that an agent is action-oriented. For example, if a user asks, "Why did this alert trigger?" a chatbot may explain possible reasons, but an agent can fetch logs, query metrics, check recent deployments, analyze anomalies, and suggest a likely root cause. So the key idea is this: a chatbot answers. An agent works toward a goal. The first important capability is planning. Planning means breaking a goal into smaller steps. For example, the goal may be to analyze an alert root cause. The plan could be fetch metrics, fetch logs, analyze anomalies, suggest a fix. There are 2 common planning styles. Static planning means the agent creates a plan once and then executes it. It is faster, but more fragile. Dynamic planning means the agent plans, acts, observes the result, and replans if needed. It is more flexible, but it increases latency and cost. Next is tool usage. LLMs cannot reliably access real-time data, query databases, execute code, call APIs, or perform transactions by themselves. So, agents need tools. A tool flow usually works like this. The LLM chooses a tool. The system validates the request, the tool executes, the result returns. Then the LLM continues. The important point is this: the LLM decides what it wants to do, but the application executes the tool safely. The system must validate tool names, arguments, permissions, rate limits, and safety constraints. Agents also need memory and state. Memory helps the agent keep useful information. Short-term memory stores current task context, tool outputs, and intermediate steps. Long-term memory stores user preferences, historical interactions, or domain knowledge. External memory can live in a database, vector database, logs, or knowledge base. State tracks the agent's current progress. For example, state may include the current plan, completed steps, tool outputs, remaining tasks, and errors. For simple agents, state can live inside the prompt. For complex workflows, state should be stored externally, like in Redis or a database. The control loop is the core of the agent. While the task is not done, the agent plans, acts, observes, and updates state. But the loop must have termination conditions. For example, the goal may be achieved. The max step limit may be reached. The confidence threshold may be met. An error may be encountered, or human approval may be required. Without stopping rules, an agent may enter infinite loops, overcall tools, or waste cost. The key idea is this: state tracks progress, and the control loop drives execution. Production agents need strong observability. We should track step count, tool calls, latency, token usage, success rate, error types, retry frequency, and final outcome. This helps debug why the agent made a decision and where it failed. Safety is even more important because agents can take actions. Common risks include infinite loops, unsafe tool calls, data leakage, prompt injection, wrong actions, and high cost. Common guardrails include max step limits, tool permission checks, rate limits, output validation, budget limits, human-in-the-loop approval, and safe fallback. Latency and cost also matter. Agents can be expensive because they may require multiple LLM calls, multiple tool calls, and long context. So we should limit unnecessary steps, use smaller models for simple tasks, cache results, and stop early when the goal is already achieved. To summarize, an AI agent is an LLM-based system that can plan, act, observe, and iterate toward a goal. The core components are planning, tools, memory, state, control loop, observability, and safety. Compared with a chatbot, an agent is more powerful because it can execute multi-step workflows. But it is also riskier because it can take actions. The final insight is this: an agent is not simply a more intelligent LLM. It is a controlled system built from LLM plus tools, plus loop, plus state, plus guardrails. Thank you.